Most lectures on logistic regression drive me absolutely nuts. They usually start with a surprise review of linear regression because it's supposed to help us understand how to model the log odds of belonging to a class using a linear function. Just like that sounded, it makes things unnecessarily convoluted. I don't know about you, but I certainly don't think about things in terms of log odds. And intuition from linear regression hasn't changed that. This is how I think about logistic regression. Let's first think of logistic regression as trying to find a threshold that distinguishes points in one class from points in another class. For example, consider a data set of people's ages and whether or not they can legally drink. What distinguishes points in one class from points in the other is whether or not their age is greater than 21. Consider a more complex example, whether or not a student will pass an exam based on the number of hours they studied for it. There is no threshold in this case, probably because passing the exam depends on more than just study time. It could depend on the length of the exam too. The threshold now is a line representing a relationship between study time and exam length. The equation of the line in this case is exam length equals study time divided by 2. We'll rewrite this equation as study time minus 2 times exam length equals 0. Although you may be less familiar with the equation of a line in this form, it's an essential step toward unlocking the secrets of logistic regression. We can interpret this line as meaning the longer the exam, the more you have to study in order to pass it. Specifically, you need to study at least twice as much as the exam is long. In practice, however, there will be exceptions to this rule, and we can't be sure that a student will or won't pass the exam with this information alone. So we'd like to convey instead a probability that they will pass. The more a student studies relative to the exam length, the higher the chance of passing. The less a student studies relative to the exam length, the higher the chance of failing. The closer their study time is to the threshold that is twice the exam length, the less certain we are of them passing or failing. That region of uncertainty around the threshold could be big or small depending on these exceptions to the rule. So how do we find this threshold, and how do we get probabilities from it? Let's keep going with the previous example, but move to a slightly more abstract setting. Let's say blue represents failing and purple represents passing. Again, we have study time and exam length describing points in our dataset. Let's just call these x1 and x2 respectively. One possible threshold in this case is x1 minus x2 equals 0. So this line means you need to study at least as much as the exam is long in order to pass. Plugging any point into that equation, we will either get a positive or negative result, which will tell us which side of the threshold it's on, and exactly how far from the threshold the point is by the magnitude of the result. For example, if a student studied 2 hours for a 1-hour exam, the result will be 2 minus 1 equals 1. All students who studied 1 hour more than the exam is long are on this line, all students whose result is 2 are on this line, and all students whose result is 3 are on this line. All positive results, i.e. students who studied more time than the exam is long, are on the right side of the threshold and would be assigned to the purple class. But logistic regression is about more than finding a threshold. Notice that there are infinitely many of the same threshold since we can just multiply it by a constant. Multiply it by 2 or divide it by 2, the line stays the same. Which makes sense. Saying study time needs to match exam length is the same as saying twice your study time needs to match twice the exam length. But for a point not on the threshold, its result will be amplified or de-amplified by adjusting the parameters of the line. The bigger the parameters, the bigger the result. When the threshold is x1 minus x2, here are the lines where the results are 1, 2, and 3. When the threshold is 2 times x1 minus 2 times x2, these are now the lines where the results are 1, 2, and 3. As we increase the parameters, points closer to the threshold get bigger and bigger results. Hopefully this doesn't come as a surprise. If the difference between a student's study time and their exam length is 1 hour, the difference between twice their study time and twice their exam length is 2 hours. But then, how do we interpret these results? Did a result of 4 occur because the student studied 4 hours more than the exam length, or because they studied 1 more hour amplified by a factor of 4? It seems more likely that the student will pass in the first case than the second case. Not knowing which is problematic. Or is it? Maybe we don't need to know. Maybe the magnitude is the likeliness. It doesn't matter how a result of 4 was obtained, a result of 4 conveys a specific and universal level of likeliness. It's more likely than a result of 3 and less likely than a result of 5. In some contexts, points close to the boundary can have a likeliness of 4. In other contexts, a result of 4 requires being farther from the boundary. I like to think of the parameters of the line not as the key to interpreting the result, but as the tool with which to assign likeliness to our data points. We're more comfortable reasoning about likeliness if it's in the form of a probability, so we'd like to convert these results into probabilities. That conversion, whatever it is, needs a few key properties. If a point is on the boundary, it could belong to either class, so we need its probability of belonging to, say, purple to be 1/2. The farther the point is from the line, the bigger the result and the more certain of the class we should be, so the closer to 0 or 1 the probability should be. Because of laws of probability, there needs to be some symmetry here, where the probability of purple needs to be 1 minus the probability of blue. So we only need to convert these results into a single probability since we can derive the other with some quick math. The sigmoid function exhibits all these properties. It's 1/2 when the input is 0, this is the result of a point that is on the threshold, and is closer to 1 or 0 the bigger the input is, i.e. the bigger the result. The sigmoid function is a special case of a family of functions called logistic functions, hence the name logistic regression. I know what you're thinking. Why the sigmoid function? Surely there must exist other functions that exhibit the same range and symmetry. What's so special about the sigmoid function? Great question. The CDF of a normal distribution, for example, looks almost identical to the sigmoid function, and using it instead of the sigmoid function actually results in what we call probit regression. We'll discuss in more detail when the sigmoid function is the appropriate choice for our data in part 2, but keep in mind that other functions that exhibit these properties exist, and if you found a new one, you could invent a whole new type of classification tool just like logistic regression. So anyway, this sigmoid function, right? Without it, we could use the results as likeliness, but it wasn't quite clear how much more likely a result of 2 was than a result of, say, 1, and whether that difference in likeliness was the same for, say, 5 and 4. The sigmoid function makes this very clear. The jump in likeliness is much greater from 1 to 2 than it is from 4 to 5. For a point in our dataset, to get its probability of purple, we first plug the point into the equation of the threshold, then plug this result into the sigmoid function to get a probability. The probability of blue for that same point is just 1 minus the probability of purple. A point on the left side of the threshold will thus have a low probability of purple but a high probability of blue. Notice that all points whose probability is 0.7 are on this line, 0.8 are on this line, and 0.9 are on this line, each of which corresponds to a specific result but is much more interpretable in this form. Changing the parameters of the line lets us control the likeliness we assign to regions of our space, which we can choose to amplify or de-amplify, letting us control how quickly or slowly we transition from predicting blue to predicting purple, which lets us grow or shrink the uncertainty region around the threshold. So we can think of logistic regression not just as trying to find a threshold, but as trying to find a threshold which generates probabilities that best describe the data we saw. But how do we know if it describes the data well? For this, we need to take a bit of a detour. Your friend hands you a mysterious coin. You flip that coin 10 times and it falls on heads 8 out of 10 times. What would be your best guess as to the probability of heads for this coin? 80%, right? What you just did in your head in a split second is solve a pretty complex optimization problem, you nerd. Although seeing 8 out of 10 heads is not impossible for a fair coin, it's pretty unlikely. It would be more likely if the probability of heads for the coin were 60%, and even more likely if it was 70%. We can formulate this as a maximization problem in order to find the probability of heads that makes seeing 8 out of 10 heads the likeliest. If p is the probability of heads, the probability of seeing 8 out of 10 heads is p to the 8th times 1 minus p squared. Technically there's a binomial coefficient, but it doesn't depend on p, so we can ignore it for this maximization problem. What value of p makes the likeliness of seeing 8 out of 10 heads maximal? Well, we take the derivative, set it equal to 0, and we get 80%. It's the same reasoning for logistic regression. We try to find the parameters of the line that make the data we saw as likely as possible. The likeliness of the data we saw is just the probability of the first data point times the probability of the second, etc. Each of which is either the probability of purple if the point was purple, or 1 minus the probability of purple if the point was blue. And these probabilities are completely determined by the parameters of the line. Let's try this with a small dataset where there are only 2 students. One studied 8 hours for a 2-hour exam and passed, the other studied 6 hours for a 4-hour exam and failed. Let's say we guess that the threshold is study time minus 2 times exam length plus 3 equals 0. What is the probability of the data given this threshold? Well, we plug the points into the linear function, then feed them into the sigmoid function, then compute the probability of having seen the data we saw. 27%. Let's see how this compares to a different threshold. Let's try our original one, study time minus 2 times exam length equals 0. This gets us a probability of seeing the data we saw of 86%. Much better. But we know that bigger parameters means more extreme probabilities. So what happens if we amplify everything by a factor of 2? The likelihood of seeing the data we saw is now 98%. So when the data is perfectly linearly separable, we could theoretically keep inflating our parameters forever and continue to improve. Okay, so we know how to compare different thresholds by comparing the likelihood of the data they each generate, but how do we find the threshold that generates the maximum likelihood? In this particular case, there's no closed-form solution to the maximization problem like there was with the coin. So we do some math to transform this maximization problem into an equivalent minimization problem that makes our computers happy. We then use a process like gradient descent in order to search for solutions. We start with a random set of parameters, i.e. a random line, and nudge these repeatedly to improve. I've linked my video on gradient descent in the description if you need a review. To recap, we've learned that logistic regression is about finding the threshold that generates a sigmoid function that best describes the data we saw. Describing the data well means finding what makes the data we saw the likeliest, which is imperfect because randomness doesn't always create data that is representative of what generated it. But this is the best we can do, and the more data we gather, the better we hope to do. This is just the nature of learning from data. By repeatedly nudging the parameters of the line in a direction that should improve the likeliness of our data, we hope to mold the sigmoid function to our data and capture what distinguishes points in one class from points in the other. In part 2, when we discuss how this works with more than 2 classes, we'll see that logistic regression isn't about finding a threshold at all. We'll discuss some limitations and pitfalls which will help kickstart a series on neural networks. Leave a like, subscribe, and help me share this knowledge around if you found it helpful.